Now let's go over optimization. And optimization is a type of problem, usually a word problem, where you're given some type of problem where you need to maximize or minimize something, usually a volume or an area, or there are lots of different ways optimization problems go. So here's a problem. Find the dimensions of a rectangle with area 100 meters square whose perimeter is as small as possible. So in our case, we're trying to minimize the perimeter. So that's why this is an optimization problem. So first things first with an optimization problem is you usually want to draw a picture. So we are given a rectangle, and we're going to say it has length x and height y, and the area is 100 square meters. So now what you want to do is find an equation for your variable. In our case, it's going to be the perimeter, so we want to find an equation for the perimeter. So the perimeter is going to equal to 2x plus 2y, because we're just adding up these. And now this is what we're trying to minimize. So the next step is we want to get this equation down to one variable, so either an x or a y. The way we have it right now, we have kind of three variables, the perimeter, x, and y. We want to get it down to two variables, where the perimeter is equal to some function of x or some function of y, not a function of both x and y. And to do that, we are going to use what's called a constraint function. And in our case, the constraint comes from this part of the problem where it says that the rectangle has an area of 100 meters squared. So that's our constraint. That has to be true no matter what we find in the problem. We have to make sure that the area is 100 meters squared. So the equation for the area of a rectangle is just x times y, length times height, and that has to equal 100. And from here, we can rewrite this perimeter equation using one variable. So now I'm just going to solve for y in my constraint. Y is equal to 100 over x, and I'm going to plug this into the perimeter equation. So that's going to give me perimeter is going to equal to 2x plus 2 times 100 over x. And that's going to equal 2x plus 200 over x. And I'm just going to rewrite that as 2x plus 200 x to the negative first, because soon we're going to take the derivative, and that'll just make it easier. So now what I'm going to do is take the derivative of the perimeter, and what we're going to try to solve is for where the derivative is equal to 0, because as we know, when the derivative switches sign and hits 0, that's when we have our maximums and minimums. And in this case, we want a minimum, so we're going to take the derivative of p. So p prime is equal to the derivative of this. The derivative of 2x is just 2, and the derivative of 200x to the negative first is negative 200x to the negative 2. And now I'm just going to write it in this form. And we want to solve for when this is equal to 0. So, move this 200 over x squared over, we get 2 equals 200 over x squared. And multiply both sides by x squared. 2x squared equals 200. Divide by 2's. X squared equals 100. And then x is equal to plus or minus 10. In our case, we're just going to keep the positive 10, since, having a negative height or a negative width doesn't really make sense. So that's just from the context of the problem. And next what we're going to do is we are going to make sure that this is a minimum, because we want this to be a minimum. So what we're going to do is we're going to solve for p prime at an x value that is lower than 10 and an x value that is greater than 10. So if I do p prime of, let's say, 5, then I get 2 minus 200 over 25, and that's equal to 2 minus 8, and that's equal to negative 6. And now I'm going to solve for p prime with a value that's greater than 10. So let's say 12. P of 12 is equal to 2 minus 200 over 12 squared is 144. And that's going to be equal to, 2 minus some value that's going to be less than 1. So it's going to be positive. So that's all that matters. As we see here, and this is sometimes useful drawing it like this, kind of a number line. Here's 0. And over here, here's actually 10. That was our x value, 10. So when we have x values that are less than 10, what we saw is that p prime was negative. So that means that the function is decreasing. And then now that we checked a value that was greater than 10, 12 in this case, we saw that p prime was positive. Doesn't really matter what, it's just positive, and when the derivative is positive, the function is increasing. Which means that if we kind of sketch our function, with 10 being here, function's decreasing and then increasing, and that's a min. So it's always important to check that the value that you got is a minimum and not a maximum, or depending on the question, you might be asked for a maximum, because when you solve for when the derivative is 0, that doesn't tell you if it's a maximum or a minimum. That only tells you if that only tells you that it is a maximum or minimum, or it could also be a terrace point. So now that we know that x equals 10 is a minimum, let's look back at our perimeter function. Perimeter is equal to 2x plus 2y. And let's look back at our constraint. Our constraint was that 100 meters squared was equal to x times y. And for this question where it's asking us to find the dimensions, we don't really need to look back at this equation. What we need to do now is figure out what y is. We know what x is. X is 10. 100 is equal to 10y, which means that y is equal to 10. And now we have the dimensions of our rectangle, which is 10 by 10. You might want to have meters. And, well, I guess that's not really a rectangle, that's a square now. But that is the solution to this problem. So once again, just to recap, I drew a picture. Then I figured out what my function of interest was. In this case, it was the perimeter. Then I solved for one variable, made sure that the perimeter was a function of one variable. In this case, I had x's and y's, so I had to solve for y in terms of x. I did that using my constraint. The constraint was the area. Plugged that back into our perimeter, or our function of interest, and then I took the derivative of our function of interest, solved for when that's equal to 0. That gave me an x value of 10. Then I made sure, using the derivative, once again, of our function, that 10 is a minimum, since that's what we're asking for. And I did that by looking for a point that's less than, by solving for the derivative at a point that's less than 10, I chose 5. And solving for a point that's greater than 10, I chose 12. We saw that the derivative was negative before 10 and positive after 10, and that told us that it was a minimum. Now that we're sure that it's a minimum, I just went back to my constraint and solved for y. And this last step really depends on what the question is. The question could have also been, what's the perimeter? What is the perimeter of the rectangle with an area of 100 meters squared, whose perimeter is as small as possible, in which case I just plug this answer back in here. But what's most important is the steps that I took here, which is solving for when the derivative is 0, and never forget to verify that you found a maximum and not a minimum, or a minimum and not a maximum.